All right, good morning, everybody. ODP 215 should be due on Monday. Is Canvas saying tomorrow? Let me double check Canvas. I pushed it back last night, and maybe it didn't take in that funny way that things sometimes don't take. So I'm showing ODP 215 is due at 10 a.m. on February 23rd, which would be Tuesday. So try refreshing your Canvas window. Okay, other people see the 23rd. Yeah, so I pushed ODP 215 back. It deals with deletion of nodes in trees, and we're probably not going to get to deletion until tomorrow. And it's just a minor ODP to practice one of the steps involved in deletion. So it's not super urgent because if deletion is the last piece of PA4 that you're going to work on, you got some time till you get there. But it's on the Linux server under /temp. You can look at the README and you can go ahead and develop the code ahead of time if you feel like it. But we're not going to talk about this notion of deleting the largest node from the left subtree probably until tomorrow when we talk about deletion from trees in general. So we got some time there. Let's see. All right. Any questions on ODP 212 that you just finished today or yesterday? So let's go back to looking at this business of traversing a binary search tree. And so we were looking at this code yesterday. It was the old insert code that we wrote, last week. But we added a new function for doing this in order traversal, a left node right, and it's basically 3 lines of action code. The first one says traverse the left subtree. The second line is print the root data. The third is traverse the right subtree. And those traversals are done by calling the LNR function. And then there's this base case which checks to see if the root is null. And if it is, then it has nothing to traverse, and so it just returns immediately. So that's the in-order traversal, left node right. We mentioned there's 2 other ways we can traverse, pre-order and post-order. So let's look at what a pre-order traversal would look like. So pre-order would be node left right. We print out the root node first. And there you go. There's the pre-order. So again, see if the root is null, and if it is, there's nothing to traverse. Otherwise, print the root node, and then traverse the left and right subtrees. And that right there gives you node left right traversal. And, it's almost identical to the in-order code. The only difference is we print the root node first, and then traverse left and right, whereas in order, we traverse left, print the root node, and then traverse right. So any questions about this? I mean, we can do the same thing for post order. You could do, right, left node if you wanted. If you do right node left, you get your nodes in reverse order. But they're all basically the same thing. And they're using this recursive definition of traversal to guide the development of a recursive implementation. So when does the printf statement actually get executed? After we've traversed the left subtree and before we traverse the right subtree. So the printf happens right here. So if I call this with an empty tree, nothing gets printed. If I call it with a tree that has a single node, which is just the root, then this will try to traverse null, which will come back right away. This will print the root, and this will try to traverse null, which will come back right away. So this statement prints the root of the tree. But if the tree happens to have, a non-empty subtree on the left, then this call will print all the stuff in that left subtree. And this prints the root of the original tree, and then this prints everything in the right subtree. So this is always just printing the root, but if there's more stuff in the tree, that happens in the calls to our traverse function when we pass it the left and right subtrees. And it's an interesting exercise to try to unwind this on paper and see exactly what happens. And I have some worksheets that I use in class normally to go through what actually happens when you make these calls to the function itself and what happens when you come back from those. And I have a feeling they're not going to translate well to an online setup. Normally I pass those out as worksheets and we work through them together, and I think my doing it and having you watch is not going to illustrate it. But I recommend trying to go through this on your own and make yourself a little tree with 5 nodes and pretend you're a computer executing this 4-line function. So you're going to check root null, it's not. You're going to make a call to yourself on a different subtree. So get a new piece of paper, write down what the left subtree is, and pretend that your whole purpose in life is to traverse that. And go through the whole exercise of doing that, and when you come back and you're done, print the root node, and then repeat what you did for the left subtree with the right subtree. Let's see, I ran through it with GDB, but it segfaulted once I got to left node right, root arrow right. Where did it segfault? So use step instead of next to go inside LNR and see exactly what line it's segfaulting at. And my first guess would be maybe you didn't check to see if the root was null. So as long as root is not null, you should be able to go into left node right, root right. Yeah, so you can come into office hours and we can screen share, and you can show me what you're doing. It's confusing sometimes to try to trace these things because it's always the same function called LNR. You got to kind of know where you are in the call history. But one thing that's useful, perhaps, so let's just go ahead and do this. So I'm going to put a breakpoint at left node right. So I've already called all of my insert functions. So let me tag this. I've already called all of my insert functions, and now I'm sitting inside my traversal code. And I'm going to use steps for a while. So this is going to say traverse the left subtree. So if I print out root, right, it's some node. If I look at what's sitting in there, that's my 10. If I look at what's in the left subtree, that's my 1. If I look at the left subtree of that, that's my negative 11,223, and the left subtree of that you can see as null. So you could use this to piece together a picture of what your tree looks like, right? But I'm about to call LNR on my left subtree, so I'm going to say step to go inside there. And now, I've called it with this root, 62A0, which, has a 1. And it's not null, so I'm going to call LNR again, and now I'm inside another reference to LNR, and my root is pointing to this negative 11223. And root is not null, so I'm going to call LNR again, and now my root is null, so I'm going to come back. If I type BT for backtrace, that will show me where I am in my hierarchy of calls. So right now I'm at line 86 of insert.c, right? Which was called from line 86 of insert.c, which was called from line 86 of insert.c, which was called from line 33 of insert.c, which was my main program. But you can see what each of these things were called with, and that can help you kind of unwind the stack, literally, of where you are. Try it with a small tree. Try it with a tree with like 3 nodes, just a root and a left and a right child. And then try it with something with like 5 nodes that just goes a little deeper on one side. And it's not necessary to do this, right? And to effectively write recursive code, we really don't want to be thinking about how this is happening inside the system. But we want to understand that at some point, right? And especially if we're encountering, seg faults in trying to write code for this, it's useful to know what's going on inside. But it's a kind of dualistic attitude, where sometimes you want to think about it in great detail, and sometimes you want to just kind of go on faith and say, yeah, this will traverse the left subtree, this will traverse the right subtree, this will print the root data. That's my whole function. Yeah, that's good. All right, so let's go on with developing recursive algorithms for trees. So the next one I want to talk about is search. And we've got, some kind of tree. And there's a root. And we want to search starting from the root for some number. And we've talked about how to do this by, comparing our number to the root. If it's equal, we're done. If it's less than the root, move down to this node and repeat. Go back to your loop and see if that's your number. And if your number is bigger than that, go over to the right, and so on. So recursion, it helps to try to find a different way to think about problems. And one way to think about a search problem is, where could this number be in this tree, right? If this number is in the tree, where could it be? And there's 3 possibilities. It could be right here at the root, in which case it's really easy to find. Just see if the root of your tree matches your number. So I could say something like, if root data equals my number, return 1. But if the number is not at the root of the tree, but it's in the tree somewhere, it is either in this left subtree or in this right subtree. And I actually know which one it would be in. If the number I'm searching for is smaller than 20, it's got to be in this left subtree. If it's bigger than 20, it's got to be in this right subtree. So here's what I can do. If my root data is bigger than my number, meaning my number is somewhere in the left subtree, let's just search that left subtree and return whatever we get from that call to search. Yeah, it's like high-low. Well, if the number I'm looking for is not equal to the root and it's not less than the root, it must be greater than the root, which means if it's in the tree, it's in the right subtree of the root. So now I can just say, let's search the right subtree for our number and return the value of that. And there is your 3-line search function. And that's almost all we need. But there's still an edge case to deal with. What's the edge case here? Null tree. If we pass in a null tree, this is going to segfault. And in fact, when we search for something that's not in the tree, we're going to keep searching subtrees, subtrees, subtrees until we get to a place where the subtree we're searching is empty. So we're often going to encounter this case where the root is null and we need to deal with that. So if root equals null, and you also notice there's nothing in here that ever returns a 0 yet. We can return a 1 if we match the root, but there's nothing to return a 0. That's your other hint that you're missing something. If root equals null, return 0. That's where it's not found. So it's a 4-line search function. If the root's null, return 0. If the root matches the data, return 1. If the number is less than the root, return whatever you get by searching the left subtree. If the number is bigger than the root, return whatever you get by searching the right subtree. And it's almost laughable code. We're not really doing anything in here. Yeah, we check to see if you match the root. Well, that's easy, you know. If you want to search for something, well, look at your feet and see if it's there. That's all that's happening here. But this is what's actually doing all the hard work. And this will, you know, dutifully go down through the tree in the proper directions at each point and either ferret out the thing you're looking for or, you know, tell you definitively it's not found in the tree. Yeah, it really does feel like cheating. And when you get to the point where you can get that feeling and smile at it because you know that that's what you wanted to do, then it's like really fun. And this is a fun way to write code, and you can start thinking about more and more of coding in this style. And sometimes it's not the right style to use. Sometimes it's very resource intensive, but it's a fun, different way to think about things, right? And you can do so many things with recursion, right? Suppose you want to find the largest number in a list. I can do that recursively. What's the largest number in a list? It's either the first number or the largest thing in the rest of the list. So basically call, you know, your largest thing function on the rest of the list, compare that to your first number, return the bigger of the two. Yeah, so exactly. When it's the right way to do it, it's really the right way to do it. And this is a really nice way to do a search on a binary tree. Because, you know, we don't have any looping in here in the form of a while loop or a for loop or anything like that. And it really kind of captures, you know, the essence of what it means to be a binary search tree, which means if you're smaller than the root, you're somewhere in the left subtree. So let's just go ahead and search that. And you could write this in one line if you wanted to be kind of extreme, right? You could do a ternary operator, root equals null, interrogate 0, colon, and then make one big or statement, right? Root data equals num, or root data bigger than num and search, or, you know, root data less than num and search. And you could make a one-line search function. There's probably a theorem that any recursive function can be written in one line or something. All right, so that's search. Yeah, so some people make it a challenge to do stuff in one line. This was my objection to Perl when I did Perl programming years ago. Everybody seemed to want to write stuff in one line, which is cool to be able to do, but not always the most readable. APL was the same way too. Yeah, so yeah, I get that. Definitely. All right, questions about this? Yeah, I've seen ODP straight from the command line. Though if you're really intense, though, you could just run the assess command and redirect from standard in and actually type in the binary code that the assess command is trying to pick up. And yeah. And then you're down to, like, you know, trying to enter things by toggling your USB port with a paper clip. And that's always good. All right, questions about this? If not, we'll go on to insert. Insert is where it gets even more interesting. All right, so insertion into a binary tree. Yeah, we totally should. Hey, speaking of record board, I've noticed people aren't playing a lot of Rogue, and that's an issue for the pride of class of 2020, 2021. Check out Rogue on the Linux server if you like. Here, we'll do a quick Rogue lesson. So it's a dungeon game, right? So so first of all, the key thing is you use HJKL to move around, so it's good practice for VI, right? And you go around and you explore things, and you can find scrolls and you can read them, and you can use that to identify things, except they don't have anything to identify. I can identify my food. But it's all kind of good, you know, Unix practice. Bats are annoying because they fly around, eat all your food. When you get to a staircase, hit a greater than sign to go down. And you can do a question mark to get help, and star will give you help on everything. And this is you know, just kind of, you're stuck on a problem, go ahead and hop into the dungeon and play around, and it's a good way to kind of clear your mind. And you got to collect gold. That's the whole point of the game, is to collect gold and ultimately to try to get down to the lowest level, which is around 30, get the Amulet of Yendor and escape. And apparently it's never been done. Oh, here's a good room. So this is filled with monsters. Those letters are monsters. And there's probably something really good in this room, but there's a good chance I'm going to die trying to take these monsters out. But got to level 2. Got to level 3. Kestrels are bad. Don't mess with ice monsters. Oh, they're following me. Ice monsters always freeze you, and you usually die. Yep. Alright, so yeah, anyway, there's the top scores, and I think these are all from last year, and there might be one from the year before that. So check out Rogue if you like. Like I say, if nothing else, it's good practice for basic Unix commands and for VI commands. HJKL for moving around helps you get away from using arrow keys. Emus can be like pretty vicious in real life too. So let's insert a new node containing some number into a tree. So here's a tree. And let's say we want to insert an 11. Well, we wrote code for this last week, and it was kind of like a search. You start at the root, compare what you're inserting to the root. 11 is smaller, so we changed our temporary pointer to here. Compared 11 to the root there, 11 is bigger, so we changed our temporary to here. Compare the root, 11 is smaller than 12, so we would change our temporary to be the left subtree, but we'd observe the left subtree is null, and so we would go ahead and we would add the 11 node down here on the left subtree. So that was our iterative approach to inserting. So how do we do this recursively? Well, here's the basic setup. We're going to have to embellish this a little bit, but here's the kind of high-level basic approach. If our number is less than root data, what do we want to do? Insert your number into the left subtree. Else, insert your number into the right subtree. Okay, that's the gist of it. So our insert function will do one of two things. It will insert the number into the left subtree, or it will insert it into the right subtree, depending on whether the number is less than or greater than the root. And that's almost it. But we do have to do a little bit of work. There's always some point in a recursive function where you've got to actually do something. You can't just make your whole program, you know, call myself to take care of this. So what's the case where we actually have to do some work here? What's the edge case? Null tree. That's almost always going to be the right answer. So our edge case is if the root is null. Alright, so if we're asked to insert a node into an empty tree, what do? We make a node, we set the data, we set the left and right children to null, and that is our new tree. So if the root is null, make a new node, so call malloc. Set the data equal to our number. Set the left and right children to be null. And this is where we need to make sure that our insert function returns a pointer to whatever our tree node is. Because we have to deal with the case where we pass null to the insert function, and the new tree should be non-null. So we're always going to return the root of the tree after we've inserted. And we take advantage of that in this case right here, where the root was null. We make a new node, set it up to be the root, and we return that as the tree, also the root of the tree. We're just assuming the number's not in the tree. We're brushing that under the carpet. Otherwise, make a decision, you know. This would insert it on the right if it was already in there, but that gets ugly and stuff, so we're just assuming the number's not already in the tree. Alright, since our function is supposed to return the root of the tree, I need these to also return the result of calling insert. Now we got a full insert function. And again, it's like 3 lines of code. So what do we do? If the root is null, make a new node, set the data left and right children accordingly, and return that node. Otherwise, if your number is smaller than the root, call insert on the left subtree to insert your number and return what you get back from insert. Otherwise, call insert to insert your number into the right subtree and return what you get back from insert. And maybe, you know, if number is bigger than that, otherwise, you know, return null or something to indicate that you can't insert because the data is already in the tree. All right, and these are the functions you want to be implementing for PA4. You want to do recursive search and insert and traversal and so on. And once you're comfortable with recursion, this is a whole lot easier to read than the iterative version, where we make a while loop and we keep moving down the tree with a temporary pointer and so on. Cool. Other questions on this? It can be very elegant, definitely. And so as you're working on PA4, I would start off trying to do this recursively. Don't even bother with the iterative version. Use it as a kind of, you know, practice area to start writing recursive versions of these things. And the more you write it, the more natural it'll start to seem. Alright, so we've got traversal, we've got search, we've got insert. Let's talk about tree height. How do you print a string held in a node? You mean other than printf? So if you have a pointer to the node, you can, you know, do your usual like that. For example, if you have a license plate information, you can just print it as a %s. Make sure you're using the arrow to dereference, you know, the pointer. But temp is a pointer to a node, so go to the thing it points to and grab the field name plate. This thing should have been declared as a car star, which is what %s is expecting. But if you did temp dot plate, or if you did star temp arrow plate, you'll get strange things. If you're getting hieroglyphics, yeah, play with it more. Try printing it out as a %x or a %d and see what you're getting. See if you can figure out from that. But if not, you know, go into GDB, stop right here before the printf, and, you know, print out what you're passing to printf inside GDB. Break it down into pieces and see if you can figure out from that what you're actually getting. %x just does a decimal number integer in hexadecimal, and it's sometimes easier to see memory addresses like that. %p will give you hexadecimal for a pointer, and then %d is just a plain integer. And if you're in GDB, you can use the examine command to actually just look in memory, and that's always sort of the most direct way to see what's going on with a variable's value. Just look at it in memory. So remember when we talked about the height of a tree, it was related to depth. So depth equals number of hops from root. So this node has a depth of 0. All of these nodes have a depth of 1. All of these 4 nodes have a depth of 2, and these 2 nodes have a depth of 3. 1, 2, 3 hops to the root. And then height equals the maximum over all nodes, n, of the height of n. So find the height of every node, and find the depth of every node in the tree, and take the maximum. And that's the height of the tree. So you can do a traversal algorithm, and as you move through the tree, you can keep track of how deep you are, and use that to calculate the depth of each node, and keep a global somewhere that records the maximum depth you've seen. And when you come back from your traverse, whatever that maximum depth is, that's the height of the tree. We're not going to do that. We're going to take an easier approach. So what's the height of a binary tree? It's 1 more than the maximum of the height of the left subtree and the height of the right subtree. So think about this kind of logically, right? How do I find the height of this tree? Well, this tree has a left subtree, and it has a right subtree. Whichever one of those trees is taller, if I add 1 to that height, I'll get the height of this original tree. And I can code that in a one-line C function which says find the height of the left subtree, find the height of the right subtree, find the largest of those 2 numbers, add 1, that's the height of my original tree. Okay, classic recursion here. And you know, we don't have a standard max function in C, but you know, write an if statement or something, or make a function called max, you know, or something like that. But pseudocode here, right? The height of the tree is 1 more than the height of the largest subtree. That's basically it. And the same edge case as usual. If the tree is null, we can't ask about the height of the left and right subtrees. Those don't exist. We can't get a dereferenced value for null. So we need to deal specially with the case where a tree is null. And in that case, we return the height of a null tree, which we said was -1. And that's why we do -1, because it makes this notion of a recursive height function work perfectly. So if the tree is null, return -1. Otherwise, return 1 plus the largest of the height of the left or the right subtree. So most of these things you're going to code up for PA4 are a few lines of code. The trick is, figuring out how to set things up so that those few lines of code actually work. But it's mostly going to just work, which is kind of cool. You got to line up your variable types, right? This has got to be an integer function so that I can take the return values from here. I can compare them in an if statement or something, and I can add 1 to it and then return that, and know I'm dealing with integers. In my insert function, I've got to be returning a pointer to a node so that I can, take the return value from a call to insert and return that as my function value. So you got to line those things up. But start writing some of this stuff. Like I say, start with traversal, right? Because that one's the most straightforward, and then build up from there. Yep, pretty much. It works until it doesn't. Now, the downside of recursion, and we'll get to this in a couple of weeks when we talk about recursive, when we talk about dynamic programming, the downside to recursion is it's kind of resource heavy, right? When we have a function called search and it's going to call any function inside here, that's an expensive operation. To call a function, we need to do a number of things. We need to save the program counter so we can return to where we were. We need to save the registers that the CPU, uses to store local values. We need to store local variables. If I have some variable in here called temp, I need to save that value because when I come back from this function call, my local variable should not have been disturbed. So there's a lot of information that has to get saved, and that mostly gets saved on the stack. But there's overhead associated with that. And it takes stack space, and if I have, 1,000 bytes of local information in here, I'm going to use up 1,000 bytes of stack storage every time that I call a function. And if this function is calling itself, and if that call is going to call itself 1,000,000 times, right, I'm going to take 1,000,000 times 1,000 bytes of storage on the stack. I'm probably going to run out of stack space. So your stack overflow, right, this is the classic case where it happens. Recursion that runs wild. How does that happen? Well, usually if you forget an edge case, right, you can get into trouble. Sometimes you'll be lucky and you'll segfault. But if not, you can just keep calling yourself over and over and over until you run out of stack space and your program crashes. With binary trees, that's usually not a problem. So think about your search function. Each time that you call search from within search, you're passing it a subtree. You're passing it either a left or a right subtree. So if my original tree looked like this, and I call search on tree arrow left, this is the argument to my new call to search. If I call search again with tree arrow right, this is my tree. It's a single node. The height of the tree decreases by 1 each time I make this call. So my tree originally had, a height of 2. When I call search either on the left or right subtree, right, my tree is going to have a height no greater than 1. It could be, 0, but, it's going to be a height no greater than 1. And if I call search on a subtree of this, it's going to have a height of 0. Or, maybe it's null and minus 1. So my depth of recursion is bounded by the height of my original tree. And even if my tree, has 100 hops from the root to the deepest node, so it has a height of 100, calling a function 100 times within itself, that's not really a concern. And a binary tree containing, node at depth 100 could theoretically store 2 to the 100th pieces of data. So if our trees are balanced, then, the height is sort of minimized based on the amount of data. and we don't go very deep in this recursion at all. But we get a huge payoff in terms of simplicity of code, simplicity of writing the code and reading the code and maintaining it. So we usually like recursive solutions. Alright, so I just said the word balance. Let's go back and take another look at balance. And we actually had a recursive definition of a tree being balanced, so let me remind you of that. A tree T is balanced if T is null, or all three of these are true. 1. The absolute value of the difference of the height of the left and right subtrees is less than or equal to 1. And the left subtree is balanced. And the right subtree is balanced. And so there's your recursion right there. So how do we code this in C? If T is null, return true. I don't know why I wrote 2. It's less than or equal to 1. If T is null, return true. If the difference in the heights of the left and right subtrees is less than or equal to 1, and balanced T arrow left and balanced tree arrow right, then return true. Otherwise, return false. So your balance function is a few lines of code. But what's happening in here is intense, right? This is you know, wiggling around through the tree and going off in all the different directions, and at each point checking to see, you know, if the left and right subtrees have similar heights and if the left and right subtrees are balanced. And this is, you know, why this works on things like this. So we check to see if this tree is balanced. Well, the heights of the left and right subtrees are exactly the same, so that condition's satisfied. But then we're going to call the balance function on this tree right here. Well, is that tree balanced? Well, first thing it's going to do is look at the height of the left subtree and look at the height of the right subtree. This has a height of 2, this has a height of -1. Those heights differ by 3. It's not balanced. So this call will come back false, this call will come back false, this conjunction of 3 statements will come back false, and so my call to balance on this original tree will return false. And it just kind of works. Alright, questions on that? So how do we delete from a tree? We're going to have the same usual 3 cases, plus an edge case. Edge case, if the tree is null, we don't have anything to do, but we're not going to delete from a tree unless we know the node is in the tree, so we don't have to worry about the null case. But basically, you know, if the number we're trying to delete is smaller than the root, delete it from the left subtree. If the number we're going to delete is bigger than the root, delete it from the right subtree. Otherwise, delete the root of the tree. And that's what we need to talk about tomorrow, is how do we delete the root of a tree. And this is the one case where we actually have to do some work. We can't just, you know, wave our hands and say we're done. We're going to have to actually do a fair amount of work, which is why deletion is the thing I said delete for last in PA for. So we'll look at deleting the root of a tree tomorrow, and then we'll, you know, jot down the pseudocode for deleting from a tree in general, which is just 2 recursive cases and the root case. Oh, are they landing today? That's right. It's the 18th. Cool. Yeah, check that out. 11:15. Oh, cool. Maybe I'll stream it in the corner of class. Awesome. Yes, Mars. Cool. All right. Have a good one, and I will see you tomorrow.